a remarkable effect. This was an experiment which was shown by Lenz, the famous Lenz law. What he did was, he took bismuth metal and indium metal, two metals, big bars, made a junction, and in one direction he passed the current. At the junction, he had put a drop of water at the junction. He passed current. The junction at which the water drop was there, it became ice. Ice. Then I reversed the current. It became water again. It is the perfect experimental demonstration of reversibility of this effect. This is what is ideal. This is so distinct from what you are normally used to when you want to build a furnace or you want to heat. Like what we had our old heaters. What is it? That is Julian heat. That is, if there is a metal with resistance R, then the amount, if I pass a current I, the amount of heat which is produced by this passing of this current is I squared R. Please remember, I squared R. So it does not depend whether you pass current from left to right or from right to left, because it is I squared R. Heat is always generated. So electrical energy is converted into heat. That is very clear to us. And it is irreversible. There is no way. In distinction to this, if I take a metal A and B and then pass this current from A to B, at this junction, it manifests as some heat is liberated from A to B. If I reverse the current, heat is absorbed. If heat is liberated in one side, heat is absorbed on the other side. This is a reversible heat absorption or generation, and it is linearly dependent on I. Now depends on the direction you pass, whether it is from A to B or B to A. And the beauty of this effect is, both the metals A and B are now held at the same temperature. I have not changed anything. Same, it is isothermal. But then if I pass current, heat is generated at the junction and heat is absorbed when I reverse. This is called Peltier. And Peltier, like Siebel, he is actually a watch repairer and a watchmaker, a French person. So he himself was not a physicist, but he did this important experiment, and it is this experiment now, it is the modern thing, we have got what are called Peltier coolers. These are Peltier local area coolers, now commercially available. I have it in my bag, which I demonstrate to a student, a small Peltier cooler. I can pass current and get a cooling. One side gets cold, another side. I can make it close to keeping a drop of water. It's a reversible. This is an effect. But this effect is important in materials, not metals, but semiconductors. In fact, this whole area of work is now gone into the area where we use extensively semiconductors. Instead of metals, we use semiconductors. Semiconductors have got a big advantage over metals. The Seibel coefficient of metals typically is in the range of 1 to 2 microvolts to something like 20 microvolts, 30 microvolts per degree centigrade. That means if I create 1 degree temperature difference, I get about a voltage generated something like varying between 2 microvolts to about 20 or 30 microvolts. Correct? For 1 degree. That is the sensitivity or the Seibel coefficient of this material. But semiconductors show an order of magnitude higher effect. Semiconductors N-type shows something like minus 200 microvolt per degree centigrade. One order of magnitude high. And semiconductors, the beauty is you can make doping either as N-type or as P-type. If it is P-type, the Seibel coefficient there in semiconductors is negative for N-type, positive for P-type. Like the questions here. In semiconductors we have no problem. The sign of the Seibel coefficient is very clear. For N-type, it is electrons, it is negative, minus 200. For P-type, where the conduction is through what are called as holes or the vacant states in a field band. These are called holes, and they are as if endowed with a positive charge. Therefore, those things in thermoelectric power or Seebeck coefficient are plus. So you now see, if I make a junction of PN junction of N-type and P-type, one is plus 200, another is minus 200. What is the difference? 400. Huge effect. These are giant terms as far as thermoelectricity is concerned. You can get 400 microvolts per degree. In fact, this is a very active area of research in material science to make newer materials with better Seebeck coefficients. You have got whole class of materials. So this is an important area in material science. And in Bangalore, in material science, our workshop, we have set up an experiment wherein you measure the Seebeck coefficient of an N-type material called bismuth telluride and a P-type material. And then you just see the effects of these big things regarding the other. You can get cooling and all that. We have got an experiment there. Go to that, but I did. And the theory why the effects are larger in semiconductors compared to that in a metal, we can understand straight from understanding of the detail the electronic specific heat. Correct? And we told the electronic specific heat is very small in a metal. Correct? Right? Effectively, the number of electrons which take part in the thermal process is of the order of kT per EM. That is 10 to the power minus 4 of the total number which is there. A small number, therefore electronic specificity is small. Please use that one. Now I can explain Peltier effect in a very simple way. That is something which is very elegant. I always like that one to convince you why heat should be generated one and why it should be absorbed. And what is the physics of Peltier effect?
How the junction is made when we join the two metals together? Whether there is special technique to make the junction?
Yes, I will tell. After this one, I will come back. Practical. Whatever. Now, please see when once now, I have no temperature difference. I am now passing current. So, there is a potential gradient. Therefore, there is a current flow from A to B. Right? Electrons, apart from carrying the charge along with it, and therefore the current, each electron also has got a heat content associated. Correct? There is a heat associated with each electron, which is here, right? That we call as our specific heat. So each electron has got a heat content. What is the heat content which has got? It is gamma T, right? At a given temperature related to the density state and a small. So electrons carry not only the electricity, but they also carry the heat. And you had got one experiment. I don't know, it was already done. Or you done this Wiedemann France law. Wiedemann's France law. You have to do an experiment where you measure the not yet. Okay. That is, you do an experiment, measure electrical conductivity of copper. You measure thermal conductivity of copper. That K by sigma T is called as the Wiedemann's. That one you experimentally verify. You measure thermal conductivity, you measure this, you get the right order of magnitude for the coefficient. Why it is so? You have got a famous statement. A good conductor of electricity is also a good conductor of heat. Right? Reverse is not true. Reverse is not true. A good conductor of heat need not be a electrical conductor. Which is an example? Time. Exactly. Diamond, if you take diamond, the value, if you look, please, for fun, go to internet, now you have got all values available. Please look at the value of thermal conductivity of this diamond at lower temperatures. It is more than that of copper. Fascinating. That's a very different process to avoid. That is thermal conductor. That is why it is used. Do you know where we use diamond and films? We make high power devices using semiconductors, wherein we pass currents of the order of 100 amperes, 200 amperes. Lot of power dissipation is there in a device that has to be dissipated away. So we made on a substrate made out of diamond because it's a very good thermal conductor. So we have got good thermal conductors, but poor electrical. But reverse, if there is a good electrical conductor, it is necessarily a good thermal conductor because electrons carry, apart from electricity, the heat associated with it very effectively. That is the Bruday's theory of metals. Now I use that. Now, what is the heat content associated with an electron? If I am passing current from A to B, what is the heat content connected with it? It has got a specific heat, correct? And what is it related to? It is related to the density of states at the Fermi energy, like gamma T. It is an intrinsic property of a given matter. Now, you please see now, electric current is the same at A and B. Same current is flowing. But the heat current associated with metal A is different from the heat current at B, because the heat current is connected with the electronic structure. Electronic structure of A is different from B. Therefore, the heat current in A is different from heat current in B. So at the boundary, that's why I make a junction. If heat is more, heat content in A is more than in B, it has to adjust itself to the value of B. What it will do? It will remove the difference between A and B. That's junction. That's all. And reverse, if it is B is less, it will absorb heat from the surface and go into A. So it is just matching the boundary condition. So it is very easy to explain Peltier effect from our fundamental electronic band structure, and you can compute them. In fact, all theoreticians who work in this field of thermal electricity, they use Peltier as a way. And you know, we have got these famous Kelvin relations, which I will show you. They are, all of them are interrelated through thermodynamics. This is reversible generation of heat, right? Due to particles. Now, I make next a circuit. This is the thermodynamics. These people like Kelvin, they were giants in physics, thermodynamics. We call thermodynamics as the laws of God. We don't care what happens to the microscopic things. It is a conservation of energy, and the second one is the conservation of the entropy in a perfect reversal. I use the first and second law of thermodynamics today. Now, I made here a junction of A and B. T1 is different from T2. Therefore, there is a Seebeck voltage, and because it is closed circuit, there is a current. And that current produces the Peltier heat at this one temperature and temperature. Correct? So one produces, Seebeck produces the current, and that current produces the heat. And if you apply the first law of thermodynamics, then the electrical energy is converted into heat. Use the two equations, you get a very nice relationship between the what is called the Peltier coefficient and the Seebeck coefficient, which is dE by dt is the Seebeck coefficient, and pi is the. In fact, you please go through this derivation because now I don't have time to do this part. But having done this, if I have got only Peltier effect and Seebeck effect, the net result what it gives is the EMF, Seebeck EMF, should be strictly linearly proportional to temperature. Ideally, I would love to have it, but practically it is not there. I must have, that is where the experiment which now I am going to is of great importance. The experiment which you are going to do on iron copper here is the experiment which made Kelvin realize that there is another effect. The greatness of a scientist is to see something beyond. He saw this experimental result of iron copper, and then he conjectured that had it been only for the normal Peltier and Seebeck, this is not valid. there is something else. Then he predicted there is another effect and then verified it. I think that is the greatness of this Thomson. Kelvin was known as Thomson. Afterwards he became Lord Kelvin. Right? So this is known as Thomson. So Thomson effect is something which is probably the most fundamental, and it is a combination of both. Seebeck is what? I create a temperature gradient. Right? I create a temperature gradient and see the effect of what happens inside. Peltier is what? I pass a current and see what happens to the thermal process. Now I do both. I have got a metal, there is a temperature gradient, and I pass a current. It's a combination of both. Then what? There is a reversible absorption or evolution of heat all along the length of the system, which depends on the direction of the current and on the direction of the temperature gradient. It's linearly related. Unlike the Julian heat, which is irreversible, this is a perfectly reversible equation, which is linearly related. So this one, he predicted it, and the coefficient is called gamma, and this is the Thomson. When once he predicted this, then you put the same equations into the closed cycle, then you get the famous three relations. This is called the Kelvin relation, relating Peltier coefficient with the Seebeck coefficient, phi equal to Ts. And gamma is the Thomson coefficient, is T ds by dt, derivative of this, and S is an interval. Three relationships comes, and we used to have this derivation in our B.Sc class. Is it there now also? Is it there? Do we do? No? Thermodynamics, unfortunately, some colleges I asked, they have stopped teaching thermodynamics, but this is a beautiful thing which was done experimentally verified. And importance of this experiment, now I come, after all, this one you can go through. Somebody asked me which are the thermocouples which are used, what are their compositions, what the range, everything like that. I listed all those. You can go through. In fact, you can things like tungsten, radium. You can go to up to 2160 degrees. Up to 2000 degrees you can go and measure. Sometimes you need to measure some temperature. So thermocouples are very handy, and we use the Seebeck effect for making that measurement. But tungsten gets oxidized, so the whole thing has to be under a total inert or a reducing atmosphere. It won't work in oxygen. It will just go away at these temperatures. So, these are all the plots. You can see, like whatever, all thermo EMFs plotted as a function of temperature. Practical thermocouples, type K, we have names, type K, type J, several things like that. Don't worry, like R, etc. These are all different compositions. Thermo EMF is fairly linear with respect to temperature. All the non-linearities are very small. There is no neutral temperature, there is no immersion over the entire region. These are all practical thermocouples. Now, we come to the example, which is the unique case where we have got this phenomenon of inversion and neutral temperature. Right. That experiment I will just show you the data. Then I come back to this slide. Iron copper was unique. In fact, it is this experiment, if you plot the thermo EMF versus temperature, it increases initially, it reaches the maximum, and afterwards the values goes on decreasing, and at a higher temperature it becomes zero again. It is 0 at 0, and again at about 540 degrees the voltage again 0, and after that temperature the sign of the voltage itself becomes changes. That is called inversion. Correct? Something changes. What is neutral? What is inversion? We have to know this. This is an experiment. This we used to do in B.Sc, but we can't explain to them the concept like Seebeck coefficient, why it is there. Now, the beauty of this experiment which you are going to do is that after doing this experiment, which is very straightforward, you have to analyze the data from this. and you get some important things connected with iron, how the Seebeck coefficient of iron is varying with temperature, and how the Seebeck coefficient of copper is varying. Now I have to understand everything in terms of the individual properties of iron and copper. I think that experimental we are going to do it. So the experimental arrangement is simple. I have got here a furnace which you see in the laboratory, which is, and this is made out of alumina tube. You see alumina A2O3. It's an insulator. It's a ceramic. It's a high temperature material. You take the alumina tube and then you wind high resistivity materials like nichrome or canthar. For this, nichrome is sufficient. Nichrome is the wire which our olden times in our houses, we had our open coil heaters. I don't know, your generation, I have seen that. Small coils which is open and round, and then you pass 230 volts, you can see the red hot thing. We used to keep our vessels. It was not safe because it used to touch, etc. Then it used to be catastrophic. But otherwise, that is how our olden times. They used to have electric thing, small heater. Now it is all concealed. Now it is safe to buy. But that is all. We are using Joule's law only. Resistance is high. I squared, we pass the current, we convert the electricity into heat. It is very easy, not very difficult. Right? So I wind a heating coil, and then the system in which I have made it is meant for safety, because I know students use it and I also know teachers use it. So we should not use for 230 volts operation. It is meant for lower voltages. So even if you touch it, nothing happens, even in the path, because I operate it just with about 20 volts, 25 volts. Higher current, we use higher current and lower voltage. Totally about 100 watts. I put about 100 watts into this. Important thing is, you are not only when you are heating it, heat should not go away by other conduction processes. Conduction, convection and radiation. These are the three processes. So I will pack it well with a thermally insulating blanket. The thermally insulating blanket is K-wood, glass wood or K-wood, they call it. So that's really like a woolly structure. It has got very good thermal conductivity. So you blanket with it, you can build your own furnace. What is difficult about it? But you have to get the right material. So get aluminum tube, you must get this blanket of cable, and then put about 10 to 15 ohms or 20 ohms resistor. Then have a power source which you always have in your laboratory. I'm going to use one of them, which is there. Then you can get inside when it's there, well insulated, you can get about 600 to 800 degrees inside the center of this. More than sufficient for all experiments, all your college experiments, including dark rooms. You can do this experiment. I will show you the construction. It was all built in my laboratory, a small furnace, just about this much height to go this. So, yes, at the center. At the center part. At the center, there is always in a furnace, it has got open ends. And there is what is called as a constant temperature zone, which is there, which is close to the geometric center. Otherwise, we use a lot of techniques are there to make it more. We make one heater, over and above that we put one more heater to compensate for the differences. We can do a lot of things. Anyway, this is a very simple thing. I built it. This was meant only for colleges. In fact, I built about when I was connected with the Indian Physics Association in Bangalore. I built about 60 such furnaces at my house.
Cost of this?
And
What is the cost of this furnace?
Cost at that time, I tell you, it's about 20 years back. For 5,000 rupees, I built this furnace, thermocouple arrangement, electronic system. We gave it to all colleges at 5,000 rupees. Of course, since I built it, there is no money involved in it. Whatever was the cost only was distributed. So it was only 5,000 rupees. If you build even for the same price now, you can build it. I will tell you, in fact, I wish probably if somebody wants to build, they should build in this place like that. It is not difficult because it is difficult to go to low temperatures. I always tell, difficult to go to low temperatures, easy to go to low temperatures. And if you think that it is so simple, not at all really. But big furnace fellows will never make you this. They want you to buy their big furnaces, which are very expensive. It costs 60,000, 70,000 rupees. We don't require them. Our masses, thermal mass of the systems environment is very small. So this is how they are arranged. Inside, I will show you after this lecture. Anyway, I will show you the thermocouple. What I have done is, I have got this thermocouple arrangement. I have got a 4-hole ceramic tube, a thin thing with 4 holes. Each ceramic again made out of alumina, thin one. Because I use bare wires, no insulation. Because this must be bare copper, iron, chromel, aluminum. I take 4 wires, chromel, aluminum, iron, copper. Why I want chromel aluminum is that is my standard thermocouple. I need to know what is my temperature. So that is the standard thermocouple. Iron copper is my experimental thermocouple. I make all the 4 wires go through and I make a junction at one point. 4 wires. It is not just 2 wires, 4 wires. I make a junction. I will show you that part. Then this part is kept at the center of this furnace. Temperature is the same. Top part which is there, I measure the voltage. One of chromel aluminum, another of iron copper. Plot it. You will get a beautiful parabolic thing. Then the analysis of this, what you also have to do is this. After doing this, the analysis is this. What this means, you take the slope of this curve, dE by dt, plot it as a function of temperature. That is physics. You plot the slope as a function of temperature. You can see here, slope is 0. That's your neutral temperature, correct? That is your neutral temperature corresponds to the slope being 0. Means that's the definition. So, if you plot that the slope is positive here, 0, and afterwards the slope is negative. Same thing. Experimentally you will get this. Right? Now, I now know that this part is the difference in the Seebeck coefficient of iron minus the Seebeck coefficient of copper. Correct? That's it. Seebeck coefficient of iron minus Seebeck coefficient of copper. Now, I give you the value of copper. Value of copper has been determined by the Thomson measurement independently. It's an absolute measurement done by independently and well tabulated. So I give you the value of copper. Copper behaves like this small value of positive, it increases linearly. And I give you this, yes, iron minus S copper. Copper is given to you. So you determine that of iron experimentally. And the physics of neutral temperature comes out very straightforwardly from this. Because at one point here, at one temperature, the Seebeck coefficient of iron becomes identical to that of the Seebeck coefficient of copper. Or the relative Seebeck coefficient is 0. So, if the two curves cross, that is all the essential message of doing this experiment. Why there is a neutral temperature? Is that the Seebeck coefficient of one decreases with temperature, iron, and copper increases with temperature. At some temperature it crosses. Where it crosses is actually the neutral. So, if only for cases like this, where it crosses, you will have the phenomenon of neutral temperature. You will not have it in practical thermocouple.
So whatever temperature we are varying, this is temperature difference of the temperature of some
at the junction. The other part is at ambient temperature.
Cold or cold junction?
There is no cold. You asked me. Yeah, I don't tell you. Normally, all thermocouples, you think that what is tabulated in National Bureau of Standards, there is a table, correct? Where you read the thermoelectric voltage and the corresponding temperature. There, it is all given with reference to your reference temperature, which is 0 degrees centigrade. Correct? But in the laboratory, it is difficult to do all that one. You must have an You must have what is called as a ice-water mixture, which is in thermodynamic equilibrium, that is at 0 degree. It's a little messy job. We don't do that. Most of it in the laboratories. What we have is the other tension is what? The other tension is effectively a room temperature. So you measure all the voltage with respect to room temperature. Then, if you know the room temperature, you can add the voltage corresponding to that from 0 degrees to room temperature. See, you see the beauty of this thermoelectricity is it is an integral relationship. The EMF, EAB, is integral from T1 to T2, SA minus SP T2, correct? T1 to T2, I can separate it out as, or 0 to T, if you want, that is my actual temperature. I can separate it out 0 to T1 plus T1 to T, correct? 0 to ambient temperature. Ambient, assume that ambient does not vary too much with over a period of time, then there is like a constant term. You can take it from here. The rest is from ambient to the higher temperature. That's what we do. Most of it. Even here you are going to do the same thing. So, having the entire anyway, you will be getting the manual. I have written up every of these things detailedly in the manual. Put it, and you get this flow, this neutral temperature. Now, this is for another system instead of iron, copper. It is easier to do it in iron, silver. But I had to go to a goldsmith and get a silver pipe. So I have got it in my laboratory angular. But commonly copper is easily available. Therefore, now this is the message. Like this will answer your question. If you take chromal aluminum, see, I have plotted by similar. You did the experiment not iron copper. I gave the value of copper. You determine the value absolute symmetry coefficient of iron. Like that, you can determine the absolute symmetry coefficient of chromal or aluminum by doing a similar experiment. If you do that, you can see the chromal is about plus 22, and then it varies over a temperature from 0 degrees to 1000 degrees centigrade. Aluminum also is minus 80, and it also increases magnitude wise as you go. But these two curves don't cross. They are like the railway lines, they run parallel. They will not cross. Therefore, there is no neutral temperature. There is no equation. Normal books, many of them have written as if that every thermocouple should have a neutral temperature. It is not true. In fact, practical thermocouples we don't want. If you have got a neutral temperature like the previous curve, please tell me, can I measure temperature correctly? What will be the problem? Suppose I give you a curve like that. Can I use iron copper to make a measurement of temperature? Can I? It also has got a thermometer. It varies in temperature, but can I use it? If I have to use it, what care I should take? Please see the curve and tell me. Exactly. You see here, the problem comes. Because now, but suppose I give this here, this value is there and this there. Two solutions are there. That's a quadratic. It has got two solutions. So if you want to tell, you have to tell not only that, you must also know this flow, whether it is positive or negative. Then whether you are lying in this part of the curve or not. Therefore, it is not a practical curve. We don't use this. But it is a beautiful effect which shows a phenomenon. And not only this effect is of historic importance because it made our Kelvin to realize that there is an important effect which is the Thomson. This experiment led to the discovery of Thomson. That is the beauty of this particular experiment. So I have got some details. I think the experimentally what you have to do is this. Measurement. Of course. I have got one more experiment which I have come to. At the back, I have got the same equipment like thermo-EMF analyzer. It's an electronic. All thermoelectric voltages are low-level DC voltages. As I told you, in all metals, typically the sensitivity is 10 to 20 microvolt per degree centigrade. So you must measure microwaves accurately. Now, this electronic system which is there, thermoionizer, is built around what is called as an instrumentation amplifier. Those you are used to electronics, operation amplifiers, for example, there is operation amplifiers. Fine. Operation amplifiers are extremely good DC amplifiers. That amplification, low level signals you can amplify, but it has got a lot of associated problems. Like it has got an offset voltage, very DC offset. And then if you amplify, DC offset can be about just 10 or 20 microvolts. But if you amplify 110, it also gets amplified back. And this offset varies with temperature and it drifts with time. These are the two parameters. It has got an offset, it varies with temperature, and it drifts with time. All these three things have to be taken care of if you design something good to handle microvolts signals. There are dedicated chips called instrumentation amplifier, which is built around operation amplifiers with a high input impedance, high common mode rejection ratio, or CMR. That means both of them can be noisy, both the two levels, but the output is zero because it rejects the noise. It's called common mode rejection ratio. Right? And DC offsets, we have done several things here to reduce the DC offsets in the circuit. It was all designed in my laboratory. We have been doing not electronic. So we can have a drift less than a microvolt. I can handle easily a microvolt. There are still better techniques. Now we do with advanced things. Like we have got same instrument amplifier. We have got say 4 channels. It measures like 4 channels, A to B conversion, 4 channels. One channel we can always short it and keep it. So all the drift of this is stored, and then my actual measurement I can decide. So that even if it varies for a time, I can take it in an advanced way. But normally, this instrumentation amplifiers, we can work, you can measure easily a microvolt level signal. Our things are usually about 10 microvolts. If you can measure 10 microvolts, sensitivity is better. 10 microvolts in chromate element corresponds to a quarter degree. So, here you will be making measurements of temperature accurate to quarter degree. That's quite good, isn't it? Right? But there are some experiments in the physics thing wherein you are required to make a measurement of temperature accurate to a millikelvin, very, very temperature. But then all is something very much more difficult. But normally this. So the electronics is that, and same instrumentation amplifier, after amplification, it displays it digitally, like 1, 2, 3, 4, 7. If I have got 4 positions. First position measures chromal element. Same amplifier. It has got a band, we call this as a band switch. It is a 2-pole 4-way band switch. You have seen DP/DP, isn't it? Double pole, double throw switch. Center one, 2 things here, each one. Single pole, double throw, double pole, double throw. DP/DP. This is something more. Double pole, 4 throws. 1, 2, 3. You can select because this is a manual system. I don't want to have 4 different amplifiers. Same amplifier, it is routed. First one I select. I do measurement not simultaneously but sequentially, one by one. So first voltage is chromal element, 1 position. 2, iron copper. 2 is iron copper, right? These 3 and 4, I have kept it for a measurement to verify another law of thermoelectricity, which is very fundamental. This is the EMF between metals A and B. Is the difference of this EMF coefficient SK minus SB operating between temperatures T1 and T2. This now I can separate it out to this. Is that clear? This is simple mathematical. What it means is this. If I have got a thermocouple made out of metal A and B, it is the algebraic sum of the EMF produced by a thermocouple A and C, and next C and B operating between the same temperatures. This one, now, what is the beauty of this relationship? This one will hold good only if this is true, that is the EMF is really the difference in physical coefficient difference. Had it been due to the nature of the contact, this would never have been valid. Therefore, this experiment I particularly like, and you are going to do this measurement. This positions 3, I have internally made the connection such a way it measures between, say, I have written chromal and it could be anything, chromal element. So it could be chromal iron, next thing iron aluminum, or you can choose chromal copper aluminum, anything. But I have made it to one particular element, probably the manual has written. So you take measurements 1, 2, 3, 4 at the same temperatures. Then you see, I think the values are there typically. That shows law of intermediate metals. That's how we here, chromal iron. I think you see here. Chromal iron aluminum. You add these two. 0.53 is the sum of this column, same as the temperature. So, experimentally, simple way. But this proves two things. Apart from verifying the law of intermediate, it also tells you that the EMF is the difference in the EMF generated to the left A and that from this. Had this relationship been not valid, this would never have been valid. Therefore, this, in a sense, experimentally, you can convince a student that here I am measuring an absolute property of metal A and an absolute property. Right? I think this experiment you will always get it. It's a simple thing. But you have to do all the analysis connected with the entire derivation which I told you, fitting up that equation by a quadratic, getting this law of that one, and I have given the iron value. Everything is given in the manual. You have to just follow it and put it, you will always get it. And then, probably the message of this entire experiment of thermo thing is, you can do out of this thermocouple arrangement, you can measure the thermo EMF of anything, any pair of metals which you think of. Standard is chromal aluminum, I use it always as my reference. Temperature is got from that. The rest is your experimental thing. I have chosen iron copper. Tomorrow, if you want to do something else, you can do. Or you can do copper constant term. That's another standard couple. And then I have used that one to tell people that if you do it in material science, there's a great history connected with this development of this material called constant term. What is constant in a constant term? The word constant term means something is constant. What is constant? We use it. It's a very important. You have heard copper constant, isn't it? But the word constant term means something. Something must be constant. What is constant? Yes, that's it. Or the temperature derivative of resistivity is very close to 0. Yes, it is of the order of 30 to 40 ppm, parts per million per degree centigrade. 30 to 40 parts per million per how it was achieved. How such a, in this world, actually, one of the metallurgists who developed this constant term, he was giving a talk. He was an Italian metallurgist. He was giving a talk. Enrico Fermi, you have all heard of Fermi, one of the giants in physics. He was sitting in the audience. He was a theoretician, so he did. But when he saw this entire work, something he told, he congratulated him. He told, in this world, almost everything changes, especially for such a range of this one. But here you have done something remarkable, something. He complimented him for this important experiment. So constant term is a fantastic material. I like constant term because it has got nice metallurgy associated with it, and there is nice science behind it. And we have set up an experiment on constant term in our material. It's more relevant to material science. What we do there is how we alloy, from alloying nickel with copper, how I change the properties. Nickel has got a very strong temperature coefficient resistance, but by alloying with copper, at some alloying like nickel 55, copper 45, you get a temperature coefficient resistance close to zero. How we do? What is the physics behind it? That part, both physics-wise it is interesting and materials wise. We have set up an experiment to tell more detail about constant term. They do a measurement. So, any doubts or anything connected with this? Yeah, of course, you can activate. Here, those who are interested in electronics, I just put a little bit. Normally, like the practical thermocouples, the EMF between temperature and EMF is E is never linear. It has got small non-linear. It's really small. It is not just A0 plus A1E, but you have got other quadratic, cubic, quadratic terms. So generally, fourth order or sixth order polynomial is used to get it. So you can take the National Bureau standard values, and then for things like chromal element thermocouple, both quadratic approximation and aquatic thing. If you use these coefficients from this one, from the measured EMF, you don't have to see the tables. Nowadays, we don't see the tables. Tables is old but regular standard because it is like using clocks tables. Earlier we used to do all that. Now, you can do the computer connectivity. You can write a small software. You measure the EMF. It will calculate all those things. A0, A1, A2, A3, A4 are all given to you. You can fit that equation, measure E, get the corresponding T. That's what is done. Has got software linearization. This is a linearization technique. We write a small software. That's what we do. Simple. But the method is simple. You have to get all the experimental data, get an equation. Now you can go to Excel, or you are used to Origin probably, or if you are Origin people or Excel. Either way, I am old fashioned. Excel. Okay, you can get the data, ask it to fit a polynomial of order 4 or this. It will give you this. Basically, experimental things. This is another thing which I told you, so that you can ask those of you who have got access to students, you can ask them to write a linearization program. Take the EMF from a thermocouple, get it into the computer, have an analog to digital converter. Our world of signals like voltages. After analog to convert digital conversion, it goes into the computer. It's pure numbers now. Get into the computer as pure numbers. Then write the software. Then you don't require the tables. You have got everything by the software. That's how we do. That's all modern things. Essentially, that method is simple. You can also write under C a simple program. Somebody told you to write Python. Write in Python C. Software is your personal choice. I used to do it as an old fashioned earlier in what is called as Q-basic, quick basic, because I started on 10th. At that time we used to do only DOS version, not in Windows. started at that time when the computers were there were no windows. We had got DOS. The DOS was very good, very rugged and no problems. Then we wrote the program in quick basic for our IISER.
So what is the meaning of NBS?
National Bureau Standards. National Bureau Standards. There is the standards tables are there. In fact, I have downloaded that entire table for you. It is there in my type K, global element. The entire thing is given. And this coefficient. I think probably, of course, we in our laboratory we devised a simple analog circuitry. I worked with analog circuits long time back. Before A to D, we were doing it especially with analog circuitry completely. We built a fourth order hardware linearization program. I generate an EMFE, then in the circuit it generates squaring, then it generates E to the power 2, E to the power 3. So add it up. It is easy to add voltages by a sum, that's what we call it as, and then speculative. You can do it also, but it involves about 20 operational amplifiers and big circuitry. Now, this is code, but now we don't do that. We simply get into the computer, then with the software, same thing can be done more efficiently than what it is. Just a method. And these are all done in a very automated way. This whole law of the experiment which you do here you take manual readings, the code, but I can do this experiment to demonstrate that what is done. Why I wanted to show you this today. In order to get the attention of students, you have to invent newer and newer ways of communicating with the students. This lecture, suppose I have to give, I can have my automated setup, put it here, and then have one projector. The experiment is going on, it will be retracing the path. By the time I finish and explain to them, I can be showing it to them. Because this is a classroom of say 100 or 150 people, this is abroad, that's what generally they do, visualization of the experiment. I got this entire experiment automated. So that it is fitted to the computer, the program, I can set my initial temperature, I can set my final temperature. I can give a rate of heat. My furnace, it heats up automatically, controls the temperature, linear rate of heat. This is just to give you a feeling that that's what automatic things can do. In fact, this part I show it to students at Bangalore. We have got a full automated setup in our geography, Indian academic sciences, wherein it is not everybody, there is nothing much you can do. No readings, no other thing. Because computer does everything. It does everything, calculate, data goes into a data file. So you can analyze it later if you want. But it does all the experiments by itself. That's how, this is to just show that how modern experiments are done. In fact, we don't spend time on monotonously doing by collecting